In this video, we will discuss a few examples of evaluating the derivatives, right? So let's see example. Let's see a couple examples actually. So what we want to do for sure is we are looking for, we want to find f prime of 0, right? If exists, right? And the first function here is given by f of x equal to, right, x times sine of 1x when x is not equal to 0, right? We know that if you are just given this function form, x cannot be 0. If you plug in 0, you get 0 in the denominator, which means this is undefined. So when you have x equal to 0, and so this function value is 0 here. By our discussion, by the square theorem, we know that this function is continuous at 0, right? So, but let's consider a few remarks. So f is continuous at 0. Recall the square theorem, right? So, which means as x goes to 0, f of x is actually 0, right? Consider square theorem, try to do that. But we want to know what's the derivative, whether the derivative exists, right? So how do we do that? If the limit exists, if the derivative exists, the derivative is a limit. So let's try to evaluate that limit. So the limit will be as x goes to 0, and f of x minus f of 0 over x minus 0, right? So that's basically the limit we want to evaluate if we are looking for the derivative, right? So now we plug in the function. So this x is getting closer and closer to 0, which means x never equal to 0, right? And so f of x will be x times sine of 1x, right? So x goes to 0 means x is getting closer to 0, but x never equal to 0, right? So the first term here is basically x times sine of 1x, right? So x goes to 0, x times sine of 1x. What is f of 0? F of 0, by our definition, f of 0 is 0, right? Then over x. So this is equal to, as x goes to 0, sine of 1x, right? Sine of 1x. As x getting closer and closer to 0, if you try to sketch the graph of this function, right? So the graph of this function, the function sine of 1x, imagine that it's like a spring but compressed, get denser and denser and denser, but always there, right? So the function value is changing in between 1 and -1 as x goes 0, either from left side or right side. So which means this function doesn't go to anywhere. So which means if the limit does not exist. Does not exist, right? So in the first case, f prime of 0 does not exist. Now let's see our second example, right? Let's change our function a little bit. B here, our function f of x is x squared times sine of 1x when x is not equal to 0. And this is 0 when x equal to 0, right? Again here, by square theorem, this function is continuous at 0, right? Now let's try to evaluate what's the limit of as x goes 0 and what? F of x minus f of 0 over x minus 0, right? Now we plug in the function form, we get this is same as x goes 0, right? Do the similar substitution, right? You get x squared times sine of 1x, then minus 0 over x. So this is same as x goes 0, x times sine of 1x. Then you can apply square theorem, right? Try to do the get upper bound and lower bound, and both upper bound and lower bound go 0 because sine of 1x is less than 1, greater than -1, right? So this is equal to 0 by squeeze theorem. So in this case, in the second example, f prime of 0 equal to 0. So this, we have two examples. The first example, the derivative at 0 does not exist, right? The second example, the derivative of this function equal to 0. So based on our calculation, so everything is good, right? So this is our fundamental way to evaluate a limit. Use our definition.